Okay, so my talk right now, FRP piping, project planning and execution. I think I'm going to lay off flanges, nozzles, and expansion joints. I think I beat up on them enough yesterday. But I mean, for the most part, I mean, surely I might recall some things that I showed you guys yesterday. Yeah, I don't see Rob in here right now, so I can beat him up. I want to specifically talk about FRP piping here because FRP tanks are really the redheaded stepchild on a lot of plant sites. Nobody knows what they're looking at with FRP tanks, but they are pretty big assets, so you have to pay attention to them. But piping is even worse, just even more of an oversight because it's all the way up in the rack. Small diameter, a lot of times, process piping, it's hard to reach. Out of sight, you just sort of, I heard this yesterday, set it and forget it from the old infomercials. So I want to go through examples here from a piping project and point out things that you would benefit you guys, things that can improve your knowledge, clarify important steps along the way, that you're not skipping over, ultimately to improve performance. So FRP, I mean, they're seen as the critical assets, right? I mean, FRP tanks. So they're expensive. I mean, they're large. They stand out. A failure obviously brings a lot of attention. But because of that, it's you often overlook the FRP piping because you're more focused on the more critical assets. Most piping projects actually require more attention, which is sort of counterintuitive, I would say. But as I've been going through this and doing piping projects, tank projects, I've just found like piping projects are actually a bit more involved than you'd think. And with this, I'm trying to explain to you why that actually is. So that's what this presentation is about, is to sort of give you an example of what a typical FRP piping project is from specification phase throughout installation, to show you some of the pitfalls, and you'll just see the variables that we were talking about yesterday with flange design. Just the variables keep adding up of why you might run into issues if you overlook certain things. So start with the obvious here. I mean, expectations of performance. Just want to do some background. So I mean, since 2020, the performance, the need to stay operating, the need for reliability seems to have increased. But for a time there, you guys were skipping outages like crazy. Just you didn't want to come down, so you just ran your plants hard. It seems to have corrected itself a bit. There are several failure investigations that we seem to be in pretty consistently when the outages were being skipped. But running hard exposes reliability issues. When the products are brand new, often there's no worries. But if you start seeing issues in year 5, and year 8, year 12, when you're expecting 20, 25, well, you're probably running it a little bit too hard. Maybe you skip some steps in specifications or engineering. I mean, some failures are just from lack of attention during operation. I'll admit that, but many are from lack of attention before a single part is even made. Failures, leaks, lost production. I mean, it's not acceptable. Can't be tolerated. When we see the earthworm piping, the patchwork repairs on your sites, I mean, that shouldn't be seen as normal or okay. Plants that run reliably are not lucky. They have a plan and they follow it. It should go without saying that failure and oversights are expensive and should be unacceptable. So here it is. I mean, I actually gave this talk last year, the Total FRP QA program. I'm not repeating it, but I'm showing how this Total FRP QA program that we are harping on a lot. Pretty much every time you talk to me or Jeff, if we come out to your site, do a lunch and learn, or just talk to you guys, we're preaching, harping on this FRP QA program. So the purpose of this this presentation is about this QA program in action. Like I said, it's not rocket science. You want good specs, including bid reviews, work with good manufacturers, and then you see QC and supervision. Well, your mind first goes to, oh well, shop QC. That I'm used to doing shop QC, but there's more than just shop QC. There's QC doing throughout the process, the engineering QC. Who's doing the design? Who's reviewing the design? Are you guys capable of reviewing the design yourself? And then, of course, you do have shop and field QC supervision. And then you just flip a switch and never look at it again? Or do you have a process for checking out your systems, whether it's tanks, whether it's piping? Can you track performance to where you can actually track, do some sort of regression study on and track your performance to try to get out ahead of issues and be proactive on them as opposed to being reactive? So in theory, it's not complex. I mean, this is pretty simple stuff, but in practice, it's not that simple because who checks all those boxes? That's a lot of different facets of the project. So who checks all those boxes? It's very rare to find somebody that can actually do all of those. Talking about specifications, the need for them to be prescriptive and descriptive, not a performance spec. I mean, we want, defining the operating conditions, service conditions, that's fine, but you need more guidance for design and manufacturing. So the greater effort you put into quality specifications, the greater likelihood the equipment, the piping systems meet expectations. You want current industry practices. These things get updated every few years. If you have a standard that hasn't been updated in 5 or 6 or 8 years, maybe it's dormant, maybe it's gotten pulled. If you can't find a current date when you're Googling what the current standards are, there's a good chance it's been superseded by something else. So do you know what that is? What we ended up seeing in a lot of your guys' specs is just like a smorgasbord of standards and every single FRP specification, standard, code known to man is in your specs, and you just hope one of them sort of fits what you're doing. But that creates a lot of vagueness and a lot of open for interpretation standards. And calculation equations, because they all tend to say something a little bit different. State all expectations. Anything left to chance is out of your control. So here's your chance. That we talked about materials, defining what your corrosion barrier thickness is, your veil, your surfacing veil material. That's where you define your flange construction. That's where you define the acceptable joint types and how you're going to handle that. Don't leave questions to be answered. If you're not providing clear and concise direction, you're going to get a ton of clarifications. You're probably going to get a ton of RFIs, requests for information, and likely a fair amount of exceptions as well. And each project is specific. I mean, there is a lot of boilerplate information in your specifications. Design parameters change, how to test change, just configurations change where you need to actually have a unique spec for each individual service that you're doing, each individual tank that you're installing. If any of these get skipped, it's usually this, where you're not qualifying experienced FRP vendors. So, I mean, here are some of the general things, just reading through these. You want somebody that has good experience for what you're doing. Are they capable? Do they look like they have it? Are they convincing you just with talking to them, by visiting their shop? Are you convinced that they can handle the piping system on your project? Are they set up for pipe? Jeff was talking about the shops earlier. Tanks, you need a lot of open space, and piping not so much. So does it look like they're set up for pipe? Do they, what does their jigging look like when you're walking through their shop? Do they have, experienced pipe fitters, or guys that are, I don't want to harp on the 20-year-olds, but it's better to have 20 years of experience for pipe fitters than just a lot of, eager young guys. You need some of the old hands and the guys that have done it before and seen it all. So specific things to look for when we're doing shop audits. Ideally, you want to do these shop audits in person. You want to look for their shop and employee certifications. Do they have them? Hopefully. What are their engineering and design capabilities? Do they do a lot of their design in-house? Do they farm it out? Do they do maybe just standard stock calculations? How good are they at doing unique configurations or unique systems? What is their current shop capacity and current workload? I would say if you go into any shop in the US these days, it's going to be very, very booked up and should be very, very busy. Are you impressed with their facility? Is it modern? Is it clean? Do they have experience with specialty resins? Do they make the resin dance? We were talking, I think Jeff was talking a little bit about yesterday. One of the 4 Jeffs was talking about the different temperatures. That if it's too cold, you do this with the resin. If it's too hot, you do this with the resin. So can they do that? Or are they just getting into a situation where they're trying to do the same thing in every single situation? And if they run into trouble, now they call the resin manufacturer. Ideally, you want the guys that they know what to do without consulting them, because that proves that they've done it a while. What is their testing capacity and shipping capabilities? This goes for both pipe and tanks. So tanks are largely standardized. I'm getting into tank versus pipe now. So tanks are largely standardized, especially flat bottom, dome top. Many non-FRP guys can pick up RTP1 because it has a lot of good cookbook, rules and equations. So a lot of non-FRP guys can just read it and figure it out for a pretty standard tank. Well, with NM2, it's made it a little bit easier, but it's still not quite there. You cannot, you can, if you don't have any experience with FRP pipe stress analysis, you're not going to be able to open up NM2 and teach yourself. It's just not going to happen. You end up, you hear the phrase, you're learned enough to be dangerous. That's truly where you're going to get if you're just opening up NM2 trying to do pipe stress analysis or pipe design without any guidance. Jeff talked about the different design methods. I'm going to show an example of the different design methods in practice a little bit later, but like I said, it's not something that you can, it's not a how-to manual. Even load combinations, it's a little bit vague in NM2. So engineering is a valuable resource, and everybody's pretty busy these days, and we are not big enough to do your entire plant design. So what are you forced to do? Who is analyzing these miles of pipe? It's the steel guys who have a bunch of steel on the project, and some FRP is thrown in, so they got to do the FRP. Well, if they're just trying to read NM2 and figure they can do FRP, it doesn't work that way. But it's hard for engineers like Maverick to sell engineering to engineers. We're a prideful sort. But in your specs, I mean, you guys can force them to do that as well. You can tell them, like, thou shalt go to Maverick to do the non-metallic. You can go to somebody who knows what they're doing. You have the ability to do that. The other thing that's interesting here, though, too, is, I mean, who's deciding what actually needs to be analyzed? There's vague rules in NM2 about, when you should do a formal analysis, when you can do a simplified analysis, but there's not like it is this temperature and above you do an analysis. It is this pressure and above you do a detailed analysis. There's combinations of the two. It depends on critical service. How worried are you about your system? It could be pretty mild pressure, for example, and maybe mild temperature, but it's a critical service to operation to keeping your plant running. So that goes up on the level of priority to where I want a formal analysis on that one. So who's actually deciding this? Like I mentioned this yesterday about the thermal expansion of FRP. If you're having steel guys who, are used to, they see 170F as nothing, we would just design this by rules for steel, you can't apply that the same way to FRP. So pre-NM2 sizing and pressure rating was a little bit less standardized, but NM2 does address that. I'm not sure how well you can see this. I tried to color code it to try to keep things a little bit together, but NM2 has added a new little wrinkle with the design methods of doing either by rules, which I'm showing here in the orange, with no testing. That doesn't show up very well. I'll read through it though. So there's just, if you don't do any testing, there's these values, understandably conservative. And then the green here is an estimated allowable as if you're doing short-term testing. So the benefit is you do short-term testing, you prove your product, you get to use a lower design factor and reduce your component thicknesses, allows you to be more competitive. Honestly, this is a pain in my butt, I'll be honest, because often we're engaged before bids have gone out. So if we're doing a stress analysis, what are we forced to choose? We're going to choose the most conservative design, the most conservative thicknesses. And then once it gets bid out, then the bidders are like, hey, we have method C testing, can we use this? Well, now we got to go back and rerun the analysis for the improved properties, the thinner walls, which is going to increase the stress. But just an example here, if you can actually read through it, I'm showing just pipe wall thicknesses from 4-inch diameter to 24-inch based on the different allowables, whether you're doing no testing or this is my estimated allowable from an actual test. And the math is just, it's linear. So the ratio difference between what I'm saying is a 3,500 allowable for the testing versus 1910 for no testing, whatever that ratio is, it's almost 2-to-1, is the difference in what the thicknesses need to be. So that's pretty dramatic thicknesses, one for cost, but also for me doing the analysis. If I want to assume my 24-inch pipe is 0.942 and you're telling me it's actually going to be made at 0.514, that's a pretty big difference. Elbows the same way, they get a little bit thicker. It ends up being about 50% thicker than the pipe. So you can just see the magnitude difference, but also at the same time, you do see the benefit that NM2 is allowing for doing short-term tests. It's going to allow the manufacturers to be much more competitive without losing reliability. So QC and engineering, the important thing here, and this is not, the load combinations are not found in NM2 unless I'm overlooking something. When we analyze FRP, Temperature is a sustained load. It is a normal operating load. We do not get to consider an expansion case and consider temperature by itself, because temperature is one of the most things, the biggest things we're worried about, right? It's the expansion. So that has to be our sustained load, because that is how your system is operating. We don't get any benefit of a secondary stress or relaxing or creep or whatever, because we don't have that ductility that steel does. So from this, understand that thermal has to be part of the sustained case. So here's just a sampling graph of different, various manufacturers' published data for ultimate strengths. It's all over the map, you can see. Some as high as 22,000, but a lot of people, are using Caesar for their flexibility analysis. They don't have an allowable. So they like, okay, Mr. Manufacturer, what's your ultimate strength? Or I'm just going to go online and look at different products, and I'll just, throw a dart and choose one that seems to work. So after seeing all this variability, how confident are you actually in the allowable stress? That's where the benefit of doing the method C testing per NM2 gains you an actual real value that you don't have to guess at. But can you trust the engineer who's only doing FRP once a year to know which allowable to choose, or even to know that, ask that question, that there's different allowables out there? So there's no silver bullet. This is sort of a summary of what NM2 is doing now, where the ultimate depends on the construction method, whether it's type 1, type 2, film and wound, what loading is on it. Bidirectional is different than unidirectional, and what type of material testing you're doing to prove your product. Here it is here where I'm saying I'm showing an example of the thermal expansion case for steel. Their allowable actually bumps up about 50, almost, and sometimes greater than 100% just for thermal loadings alone, whereas we have a modest 10% increase, and that's in combination with dead weight from pressure. So other things in your purview, you have scope changes. What is the effect on one another? Talked about that yesterday with the external loads. What do you do at that nozzle connection? Material changes. Sometimes you're connecting to a steel tank. Sometimes you have steel pipe connected to an FRP tank. Paying attention to thermal expansion in the piping in the vessels. What is the SIF? What is the K? So this is very, very important for an FRP stress analysis. There's not one cookie cutter, one size fits all approach for this. There's even more of a can of worms on axial direction versus hoop direction. We can talk about that later. I'm not going to talk about that now. But I mean, who's responsible for this? This tends to be a little bit of a black hole that NM2 is trying to solve, but it's still a relatively new standard, so there's still things that we're learning. So shifting to shop QC, we just talked about the engineering QC part. So before any parts are made, large projects are very attractive. Everyone wants it, but don't put all your eggs in one basket. Share if the schedule is tight, and who does what well, who uses different resins well, what type of constructions are they familiar with doing? Do they do dual laminate? Do they not do dual laminate? Do you know they're capable? Or if you find this out later, that definitely puts you in a bind. It's a pinch on an owner to accept calculations if the engineering and fab are concurrent. But notice here I say engineering should be complete. We talked about this yesterday. It's not an engineering shall be. As much as I would like to say that, engineering really should be complete. Laminate testing definitely helps to prove their product, and we've talked a bunch about the ITPs and different testing plans, and then also determining any shop versus field work. Where are you hydro testing it? Are you asking them to do that in the shop? Is it going to be in the field? What can be done? I said yesterday, the best field joint is one that you don't have to make. So plan your project accordingly to do as many shop joints as you can. I mean, just real quick, not going to dwell on this, but the different types of QC practices we're doing when we're going into shops, whether it's piping or tanks, I mean, there's slight differences for each one. The environmental surveillance we talked about, reading the dew point, making sure they're using the right glass. Is it conditioned well, or are they letting it, just sit in the open shop there? Making sure the dimensions are good, doing barcoal hardness testing. This is similar to the shore hardness testing that Rob was talking about, but it's a different tool for that. You can determine glass content from core samples, and you can also do physical material testing to prove the product. Getting into the actual part of the presentation, where we're doing some practical discussions here about why pipe tends to be a little bit more difficult than tanks. All right, you can measure the thickness of the pipe, no problem. Here we're measuring the corrosion barrier thickness, no problem, but that's easy to measure. You can measure the OD of the pipe. Well, why is that? Why would you need the OD of the pipe? Because the OD changes, as Jose talked about in the last presentation. That OD is very, very important to us when we're designing pipe supports. So we need to measure that on every single spool. Hopefully it's a pretty controlled process. If it's hand layup, it may not be as controlled. How do you look inside pipe? You can get inside tanks, no problem. You can look at every square inch of the corrosion barrier on a tank that was just made. Piping, not so much. So that's trusting the manufacturers. You can send a bore scope down every single pipe in their shop. We don't do that. You want to make sure you're working with people that you trust, that are making good product. You watch them while they're doing it, understand their process. Okay, so now we're looking here. That's a lot of individual spools that are sitting down there that have just been made. We're used to just one big tank to look at, right? If we're looking at just on a surface area comparison, looking at a tank is very, very easy versus a bunch of different pieces of pipe, bunch of different components. You have to check overall dimensions. You're checking alignment, flange squareness. Are the flanges two-holed? Are they going to bolt up to whatever they're supposed to bolt up to? Are the supports and joints laid out with consideration of each other? Does the person making the pipe know where the supports are supposed to go? If they don't, then you're liable to get a joint where a support needs to go. So you need to pay attention to that. And you can see on the one on the left, you have shear collars there that are pre-installed. So this manufacturer knows where the anchor support is supposed to go. So there's some good cohesiveness between the engineer and the manufacturer on this one. Okay, now, such a small spool, but you got some funky turns there. You got some T's, tight routing. That's going to be a little bit more of a stress issue. So you have to check flange flatness, flange squareness, flange alignment. There, honestly, just in this short little spool, there's a whole mess of things that can go wrong. Okay, I said I wasn't going to beat up on flanges anymore, but a call back to yesterday. Remember this slide, just to reinforce this message that you don't know what those flanges look like that are already installed on your spool. Once it's built, you don't know. Which one of the three was it? Hopefully it was the middle one. I happen to know it was the middle one, but you don't know after it's been made. So work with good manufacturers, because it would be bad time find out your flanges were built wrong after it's already failed. No way to know. So back to this spool, looking at the quality of joints. A lot of joints means what? A lot of potential leak points. Also, we have this tight routing that is just, from a stress analyst, you look at this and you just cringe a little bit. Because thermal expansion, you don't have much flexibility in that at all. But what I want to show here is just counting this up. In this one short section, 17 joints in this small spool section. Add on to that the flange alignment and the squareness and the two-holing. That's a lot of potential issues just in this one little spool. Well, there's also probably 50 to 100 of spools that they're making. So multiply that by the joints. There's so many joints, so it should be starting to make sense to you guys of where the potential problems are, why you have nuisance leaks, just because there's so many potential leak points here. It just takes one bad one, and now you're going to have some issues. So that's why you got to make sure you're working with good guys and have good specs, good procedures. Remember this slide. When you present 3 times, you have the benefit of being able to sort of tell a whole story and reinforce the message and have callbacks to things that are important to you. But would you like bonder certifications now when you see 17 joints on that tight spool on the last slide? I would say bonder certifications are a very good idea to make sure that all those joints are done well. Because we're not inspecting 100% of the manufacturing, of the making the spools, of spooling it together. We're not looking at all that. So, and I don't know that their QC guy can really look at all that either, because there's just so much going on. So you look at joints, maybe before the preparation, maybe look at after a stage is on or after it's done and look at it. But there's, not 100% surveillance on that. So in a lot of respects, you're just trusting your bonder. All right, so it's been made in the shop. Definitely has its own challenges, but installation is a different animal. Shop is difficult, but field is just, it's completely different. It's many of the same challenges, but then you have a few more added in. It was talked about yesterday, access to the joint. I think Jeff mentioned that. You have to navigate structural steel to get in there. Do you have room to do the welds? Do you just have general access to it? Not even talking about fit up and trim and supports and flanges. And now imagine dual laminate trying to do this. That's just another wrinkle on top of that. So all of this is sort of building the case for, like, you guys should be understanding, like, okay, that's why I need to pay so much attention to this. Getting a little bit deeper just to illustrate this. You see all those tags? Well, those are all flange connections. Okay, I mean, more numbers here, and keep on going, keep on going. I mean, I counted 23 from what I could see. There's more than 23. There's some hidden by pipe, hidden by steel, scaffolding, whatever. But so there are more, but 23 flange connections that they have to bolt up, torque up, do it in sequence, come back an hour later. So you can imagine that they might want to skip a little bit and cheat and go quicker and not follow the proper procedures if you're not paying attention to them. Remember, this is just one small section of this piping system. You would look at this in operation, just walk by it. You wouldn't give it a second thought if you saw a system like this when you're walking through your plant. But there's so many things that are going into installing them that could potentially go wrong, so we need to pay attention to those. In comparing with a tank, installing a tank, much more just, I would say, logistical when you're installing a tank on a site. I mean, you set it on the foundation, you anchor the hardware down, you connect the piping equipment, you have some flanges, not a ton of field joints. So honestly, you don't need as skilled of FRP labor when you're doing tanks. But if you had a tank with, let's say, 100 flange connections, or maybe 50 joints to do, or 200 supports to put off of your tank, that would take a lot more effort. That would take a lot more expertise with the FRP guy. But that happens in every single piping system. But tanks are, by and large, a lot easier to install. So another callback to a slide yesterday. Now with those 23 flange sets there, would it be a good idea to have, some travelers with that, the desired torque, the procedure of doing a certain percentage, in a crisscross pattern, somebody initialing, proving that they did that. I mean, the old saying, like, it's never time to do it right, but there's always time to do it twice. I hate that, as an engineer, but a lot of people just, would bypass that to go very, very quick to get those 23 flanges torqued up as quick as they can just to move on. But what's the potential cost impact of not doing this? So joints, they're installed, great. Flanges are torqued. We're good, right? I mean, that's it. We're good. I mean, now we have more. We have supports to deal with. Jose gave a good talk if you were there at that last one. I mean, the need for shear collars on anchors, the need to set your gaps right, the need to anchor your supports down on the ones that need to be anchored down. I mean, this is all implementation of analysis. Tanks, they don't have to deal with this for the most part once it's on site. You better have someone installing who knows what the supports are there for. Do they know where the right supports are supposed to go? You can't just indiscriminately just add supports anywhere you want to go just because it was the nearest shoe you could see, so you're just putting on this pipe. So you can see that one fits pretty well, the need to have a good fit to the OD. But if you, let's say this was supposed to be an anchor, and you forgot to put shear collars on it, all that front end work with good specs, good manufacturers, pipe stress analysis, it's invalidated because that thing's going to rock back and forth when you have a thrust on it. The other thing I wanted to mention here is about trim allowance. Most systems come with about 3 inches of trim allowance on the end of the pipe. Not everybody likes to cut off that trim allowance when they're installing because that's an extra step, right? So then you start at one point, and you'll just leave the trim allowance on one, and then that'll sort of add up to down the line. So you need to work with people that know what they're doing because you're stressing the pipe more than you have to or more than you should if you're not taking out that trim allowance. Haven't even really talked about the expansion joints and tie rods. That's just another element to interesting piping installation. Spring cans, the cold load, the stop, everything I talked about yesterday, that's all on the installer. That's all on the operator to be paying attention to that. That's a lot of things to be paying attention to. When do you hydro test this? Do you do it in the shop or are you doing this in the field, and how are you going to do that? Just with all of these variables, I mean, this could be a big mess, and there have been big messes because not all of these things were properly considered. Another callback, remember this slide? I mean, this is what happens when shear collars are missing, or when anchors aren't welded down, or guide gaps aren't correct or forgotten to be installed, or pipe stress isn't done. Like, this is the realism of forgetting those steps to where you break that pipe on the left. Like I said yesterday, that's a lot of load to break that pipe. So that, you don't have a shear, simple as 2 shear collars on an anchor could do that. My final callback here, you have this real good savvy analyst. He specified spring cans. They're perfect. His system is perfectly optimized inside of his computer. But now it's on the installer It's on the plant to operate correctly, the plant to know what to do during shutdown when you're emptying the pipe. Remember, this was the one yesterday where that spring, they unloaded it, they lost their cold load, and it opened up their spring and moved their pipe. So that's just another element if you're throwing spring cans in there. So, I mean, hopefully I didn't scare you guys too much, but hopefully I conveyed enough, of the challenges, the different variables going through the process that are all controllable. They just take effort. They take time. They take money. They take engaging the right people, not doing it as fast as you can, as quick as you can, not treating pipe like it's just some simple material you're just buying off the shelf, sticking in the pipe rack, joining up, bolting it up as quick as you can, and just turning on your pump and letting it go. Can't do that. Don't need to restate this, but this is the total FRP QA program, finishing with actually going through and paying attention to it in the field. But like I said, success does not happen by accident. The successful owners, plants, they're not just lucky, they're doing it right. So don't let the smaller diameters and lower cost fool you. Piping needs just as much, if not more, attention than tanks. So thank you. Any questions?